let's practice writing Lewis structures. So for each of these followings, I'm going to go over 2 of them, and then I want you to try the last 2 on your own, and then we can double check it when you turn your worksheet in. So let's do the first one, phosphorus trihydride. So again, it doesn't really matter what order you go in, but I always like to start with knowing exactly how many electrons I have total. Phosphorus has 5, hydrogen has 3, but has 1, there's 3 of them, so 3, so I have 8 total valence electrons. Now, phosphorus will be my central atom for 2 reasons. One, there's 3 hydrogens and only 1 phosphorus, so it makes sense for phosphorus to go in the middle. And the other reason is that phosphorus has 5 valence electrons, where hydrogen only has 1. These 5 valence electrons make it very easy for phosphorus to bond 3 times. So then my hydrogen will bond here, here, and here. So then, let's just actually go through the list because they're pretty fast. Sulfur dichloride. Now sulfur is 6, and each chlorine has 7. 7 times 2 is 14. 14 plus 6 is 20. Oops, I forgot. Before you move on from your Lewis structure, 2 things you want to make sure. 1, is it octet satisfied? And then 2, is do you have all the total valence electrons? Now, we talked about this already in class. All elements want to have 8 valence electrons except hydrogen and helium. Since hydrogen and helium both only have an s orbital, they can occupy only 2 electrons, which is a duet. So therefore, each hydrogen is satisfied, 2, 4, 6, 8. Phosphorus is satisfied, and I have my 8 electrons. Now, for my 20 in this structure, which one will be my central? Well, sulfur has 6 valence electrons. It can bond twice. Chlorine has 7, so it can only bond once. Makes sense for sulfur to go in the middle with the 2 chlorines on the outside. Then, if you would like, you could draw your extra electrons around each atom. And then you'll see sulfur will bond here and here. Each of these have an octet, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and my 20 electrons. Moving on. Carbon, fluoride, and chloride. So I have 7 here, plus 4, plus 3 times 7. So that's 21 plus 11, which is 32 electrons. Which will be my central? Well, carbon has 4 valence electrons, right? It's in group 4. And each of these both only have 7, so they can both only bond once. So it makes sense for carbon to go in the middle and the fluorine and chlorines to go around. If you fill all your electrons on each element, now again, you can first just connect the elements together in your skeletal structure and then write your electrons. It doesn't matter. Here you can see, boom, 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 boom. Everything's connected, 2, 4, 6, 8. Each element has a complete octet, and you have your 32 electrons. Now, last one is looking at your last structure, where you could maybe have more than one central atom. Not exactly sure. So carbon can make 4 bonds. We know that. It has 4 valence electrons. Hydrogen can make 1, 3 of them. Nitrogen is 5, and then this hydrogen has 2. So how many electrons do I have? 14 electrons. Now, since carbon and nitrogen can make most of my bonds, I'm going to write both of these next to each other in the middle. Carbon 4, nitrogen 5. Then, I know that carbon and nitrogen absolutely have to bond together because it's one molecule. Well, now I still have 3 hydrogens and 2 hydrogens left. Well, if I look at my nitrogen, I only have room for 2 more bonds, so it makes sense for those 2 hydrogens to bond to the nitrogen here, and those 3 hydrogens to bond to the carbon. Now we double check. Each hydrogen is bonded, so it has its duet and it's satisfied. Carbon, 2, 4, 6, 8. Nitrogen, 2, 4, 6, 7, 8. Everything is satisfied with the octet. We have 2, 4, 6, 8, 10, 12, 14 electrons. Perfect. So again, you can first draw your structure, connect the dots, and fill the electrons, or you can have the electrons and then make your bonds and rearrange afterwards. Resonance and formal charge. So for some molecules, you can actually have more than one possible structure, and that's called resonance. This usually happens when you have double bonds or triple bonds, and these can exist in multiple ways. And I'll show you an example of that. A great example would be ozone. So take a moment to draw the Lewis structure for ozone. What will that look like? So I know there's 3 oxygens. Each oxygen has 6 electrons, so I have 18 electrons in total. Now, there's no central because they're all the same, so I have oxygen, oxygen, and oxygen. If I draw my 6 valence electrons around each, I know that I'll have my 18. Now I can make a bond right here and right here. However, I have this electron alone and this electron alone. Well, I can make a bond here and then here. So let's clean that up to see what it looks like. I'm going to draw it up here. So I have oxygen with my lone pairs, my double bond, lone pair, double bond. Make sure I have my 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, great. Now double check octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10. Now that is not octet, that's more than octet. Oxygen's electron configuration is 1s2, 2s2, 2p4. It has in its outer shell s and p orbitals. Now it can have up to 8 electrons because the p orbital can gain 2 more, but it cannot have more than that. So this is not the correct structure. How can I fix that? Well, this is where that rearrangement of the bond comes in that we haven't really seen yet, but we slightly talked about in class. So because these electrons are being shared, and they're the same in electronegativity, I can push the electrons from this bond onto this oxygen atom, and I would get this structure. So now I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 6, 8, 10, 12, 14, 16, 18. Everything satisfies the octet, and I have my 18 electrons. Awesome. Now my structure's actually happy. However, there's a new problem. Why can I say that only this bond would form its electrons and push the electrons over to the other oxygen to satisfy octet? Well, I can't say that because it could also be this bond. So therefore, I have a resonance structure, meaning multiple structures. The way that's drawn is 3 double arrow, and then you would do it on the other bond. This is your resonance hybrid. It's where the resonance structures came from, where these are your most stable structures. Now we're going to learn next, later on with formal charge, of how to choose which structure is the best. But note that if you have to satisfy the octet, you rearrange your structure to make sure you use all of your electrons and you have an octet. And then if you have something where you moved one bond and not the other, you're going to have multiple structures. And this would continue until you've used all your possibilities for resonance. This brings me up to the exceptions. So for oxygen, we had to rearrange the bonds because oxygen only has s and p orbitals, so it can only have up to 8 electrons in its outer shell. Now there's 3 exceptions to the octet: an odd number, less than 8, and more than 8. Looking first at free radicals. These happen when you have an odd number of electrons. Molecules and ions with odd numbers of electrons in their Lewis structures form free radicals. That term radical means it is going to constantly react with something because it has an unpaired electron that really wants to bond with things around it to become more stable. A great example of this is nitrogen monoxide. So if we draw the Lewis structure of nitrogen monoxide, you can see that you can make a bond here and you can make a bond here. But you have this unpaired electron on the nitrogen. This is that exception to the rule because you have absolutely no more electrons. There is no charge, no plus or negative, that can tell me to gain or lose one of these electrons to make it stable. This is a free radical. So what nitrogen monoxide does, it constantly reacts with oxygen to make nitrogen dioxide, which will then react with water to make nitric acid. So basically a chain of reactions happen with the surroundings, knowing that there's water and oxygen constantly in the atmosphere, to make nitric acid, which is a stable compound satisfying the octet. Now, the other two exceptions are the incomplete octets and expanded octets. Incomplete octets is when you have less than 8, which would be in period 2, lithium, which only has 1 electron in its valence shell, beryllium, which has 2, and then boron, which has 3. Now, the reason that you can't have any more than 8 is because if you only have 1 electron, you make 1 bond, you don't have any other electrons to have more. 2, 3, etc. For BF3, boron has 3 valence electrons, 1, 2, 3. It can only have 6 sharing, no more than that. Now, elements in the third row of the periodic table can have an expanded octet. When n is equal to 3, we've learned that L, since n is the size L of the orbitals, can be 2, 1, and 0. 2 represents my d orbital, 1 represents my p, and 0 represents my s. Now I know that the d orbitals can have 10 electrons because there's 5 orbitals, the p can have 6, and then the s can have 2. Now for period 2, you only have s and p, so you can only have up to 8, which was the rule with the oxygen. However, when you get to the third row on the periodic table and below that, you have the d orbitals, so you can have up to 18 electrons in your valence shell. Therefore, you can have an expanded octet. Now, that we know how to draw Lewis structures, we know all the exceptions, how do we decide, and the resonance, how do we decide what's best? Well, that's done through something called formal charge.